Hey physics kids, Mr. C here, and we're going to talk about our last sort of topic in two-dimensional 2D kinematics and forces. And really, it's nothing new. It's nothing you don't already know. We just have to analyze it a little bit differently. And we're going to talk about forces on an incline. So here we have our little skier friend. He's chilling out on an incline, and we want to know, what does the free body diagram look like? Well, the way we do inclines is we have to define our axes a little different. So whatever our incline is, we're going to call that the positive x-axis. And then we're going to call our y-axis straight up from our incline. So it's going to look like that. So that's what our x and y-axis looks like. So if we actually kind of look at it, we draw our free body diagram right here, and I'm going to draw it in another color just so we can see it a little bit better. But we actually have, so in this case, we have whatever that tension force is pulling us up. We have our force of gravity, which acts straight down. And then we have our normal force, which is always going to be perpendicular to whatever our incline or whatever our surface is. So this is actually what the free body diagram is going to look like for this. So notice you can redraw it if you want to. So like if we redrew it over here, we could have our normal force, we have that tension force, and our force of gravity is going off at an angle like that. And remember, we always set our x-axis to be whatever our incline is. That's very important. That's just how we do it. I mean, we can set our axis to whatever we want, but it will make solving problems easier if we set our x-axis to the incline, and our y-axis is basically along that normal force. This can sometimes make doing gravity or breaking up gravity a little bit tricky, because now our gravity force basically has an x component and it has a y component. So how can we sort of figure out what these component is? Well, if you remember from our summer homework, we had that whole thing where it's like we had the triangle here, and then there was that other triangle like this, and we wanted to prove this angle is the same as this angle. And that's actually because we want to use it in whenever we talk about basically inclines. And what we know is that the angle right here is the same angle as our angle of incline. So if we kind of look at this, we can look at it and say, okay, well, we know that our sine of theta is going to be equal to whatever our opposite side is over our hypotenuse. Or in this case, the opposite side is that side that we label as f parallel divided by whatever f is. And we know that cosine of theta is equal to adjacent over hypotenuse, or that perpendicular component, or this guy, divided by f. And if we look closely, the way that we defined our axes, we define that as our x-axis and that is our y-axis. We actually see that with inclines, the sine of theta is going to be equal to that fgy over f, and our cosine is going to be, fgx over f, and fgy over f. So it's very important that we take into account what our sides are. So we basically know the main part here is that our angle here, the angle of our incline, is the exact same as that angle between that perpendicular component of gravity and the force of gravity itself. And using that, we can define that this is fgy and this here is fgx. And we can use that information to basically determine what the components of our gravitational force are going to be. So we actually want to work a problem on an incline, and we have a wooden block of mass m is at rest on an inclined plane sloped at an angle theta from the horizontal. The block is located at a distance d from the bottom of the plane. So basically, like if we just kind of draw a quick picture here, we have something that looks like this, and we have a block that's placed here, and we know that this distance here is some distance b, and this angle here is angle theta. And we want to answer these questions. We want to know what the free body diagram looks like. We want to find the static friction force for theta 0. So that's what this theta is here. So theta 0 is our initial angle. And then we want to know if the angle is increased as the block begins to slip at an angle of theta max, what is the coefficient of static friction? And then we want to finally find out is if the block slides to the bottom at this angle, what is the coefficient of kinetic friction? So, one, we want to draw that free body diagram. So remember, we're on that incline here that kind of looks like this. So our free body diagram is going to look like we have that normal force. We have, we have our force of gravity. And in order to balance out this sort of x component of our force of gravity, our frictional force must point up the ramp. So we're trying to slide down the ramp, so the frictional force must point up the ramp. So now I want to know what my static friction force is for theta 0, or this theta here. And basically all I know is that we're at rest. So my F net x is going to be equal to 0. But I also know that F net y is also equal to 0 because I'm not moving in the up or down direction either. So if I look at F net x, that's equal to the sum of my forces, which in this case is going to be that frictional force, which in this case is static friction, minus my force of gravity in the x direction. And my F net in the y direction, which is 0, is going to be equal to the normal force minus the force of gravity in the y direction. If I remember correctly, we know that this is that FGX, and this here, if we kind of trace out our angle here, is going to be FGY. And if we look at our trig, we can look and we say the sine of theta is equal to opposite over the hypotenuse, or in this case, that's going to be FGX divided by FG. And we know that the cosine of theta is equal to my adjacent side over my hypotenuse, or FGY over FG. So if I go ahead and plug that in, I say, okay, here I have that my Fs is going to be equal to my force of gravity in the x direction, which if I look closely, I can say, okay, Fs is equal to Fg times the cosine of, times the sine of whatever that theta 0 is. And in this case, that's what my frictional force is going to be. There's no formula for this because remember, we're not at that maximum static friction yet. We're just at some value of static friction, in which case, if we're not at maximum static friction, our static friction force is just whatever our whatever force is needed to cancel out our other x forces, which in this case, the only other force in the x direction is that FGX. The next thing I'm going to do, so now I rotate up my angle. I rotate that ramp, and now the angle's big enough so that I just barely start to move. That means I've reached that maximum static friction. So I know that I have that maximum static friction. So now I want to know basically what is that coefficient. So if I look here, I can say, okay, well, my F net in the x direction is still 0. And my F net in the y direction is still 0. So I'm going to have the exact same equations I had before. So I still have that Fs max in this case is still going to be equal to Fgx. And in this case, I know that my my Fn is going to be equal to that force of gravity in the y direction. I also know, so basically I know this, I want to find out what that static coefficient is. So I know that my maximum static friction force is also equal to that normal force times my coefficient. Because these are both the same thing, I can actually set that and say that, well, Fgx is also equal to my normal force times that coefficient of static friction. Or the coefficient of static friction is going to be equal to the force of gravity in the x direction divided by my normal force. But I need to know what my normal force is, which I actually find using that F net y equation. I know that my normal force we determined earlier is going to be equal to that Fg times the cosine of whatever theta max is. So in this case, I can go ahead and plug everything in. I know Fgx is Fg times the sine of theta max, all divided by Fn, which is Fg times the cosine of theta max. Or I can simplify this and say, well, Fg cancels out, and I have the sine of theta max, all divided by the cosine of theta max. Or we can simplify that further and say that's really just the tangent of theta max is going to be equal to whatever my coefficient of static friction is. Very cool if you ask me. So, and then finally we have D. So if the block starts to slide at the bottom, if the block slides to the bottom in T at this angle, what is the coefficient of kinetic friction? So we know that it takes time t, that was worded badly, but it takes time t for this block to basically slide to the bottom of the ramp. And we want to know what the coefficient of kinetic friction is, which means you really need to know what that. So in order to know the coefficient of kinetic friction, we know that the kinetic friction is equal to the coefficient of kinetic friction times our normal force. So in order to figure this out, we already know what the normal force is, but we need to figure out what this kinetic friction force is going to be equal to. The way that we're going to do that is basically, once we start sliding, we know that F net in the x direction is going to have to be equal to ma, which has to be equal to, in this case, that the frictional force minus FGX. And in this case, I'm going to go ahead and put a minus there because we're sliding down the ramp, which in this case is going to be the negative direction as we sort of defined it already. So I'm looking here, I say, okay, well, MA, blah, blah, blah. I need to basically determine, in order to find out what that frictional force is, I need to know what my acceleration is. How can I find my acceleration? Well, I'm going to think about this and I'm going to say, well, I'm going to have to use kinematics. And I know that as I'm moving down that ramp, I'm going to start at rest. So I know that V0x is equal to 0. I know that VFX, we don't know what that is. I know that my time is equal to time. I don't know what my acceleration is, but I know my distance is equal to distance. So I look here and I can say, well, I have that delta x is equal to V0t, 1/2 at squared. Goes to 0, I say my distance is equal to 1/2 at squared, or my acceleration is equal to 2 times distance divided by time squared. And that's what the acceleration of my block is going to be. Remember, it's going to be negative because we're going in that negative direction there. We're going to go ahead and plug that in. We have Fx is going to be equal to Fgx minus that mass times 2d all divided by time squared. Or my force of friction is equal to Fg sine of theta minus 2md over t squared. I can go back here and I say, okay, all of that has to be equal to my force of kinetic friction times my normal force. And I can say my kinetic coefficient is going to be equal to Fg times the sine of theta minus 2 times mass times distance over time squared, all divided by the normal force. And if we remember, our normal force is equal to that y component of gravity. So Fg times the sine of theta minus 2 times the mass times distance over time squared, all divided by Fg times the cosine of theta. And this is going to be what our coefficient of kinetic friction is. And if we actually look at this equation compared to this equation, we find that if we can kind of simplify this actually if we wanted to really saying that that coefficient is going to be equal to the tangent of theta minus 2md over Fg cosine of theta times t squared, which means that this coefficient is always going to be smaller than my coefficient of static friction, which is correct. We can go over this problem again in class if you want to, but go ahead and answer that video check problem. I will see you all in class tomorrow. Let me know if you have any questions.